Okay, so in this talk, we are going to go over the theory of how do we statically quantize a PyTorch model. And in particular, we are going to be looking at eager mode. Um, and for some background on this, PyTorch has a bunch of different quantization frameworks. It's actually kind of funny. Like, it has the oldest one, and the one that probably is going to look the most familiar to the typical PyTorch user is eager mode. Eager mode, as you can imagine, it runs like most of PyTorch does in eager mode. And eager mode, you can do a lot. However, it does have some pitfalls which make eager mode kind of dangerous. And I personally would not use eager mode without really robust unit testing. And I'm going to talk way more about that in a future video. But then PyTorch also introduced another kind of quantization, which is called FX graph mode quantization, and it leans into what PyTorch has kind of been becoming in recent years, which is more graph-based, because they wanted to do a lot more optimization on the computational graph, very difficult to do in eager mode, and so they kind of, they tried grid tracing and then torch scripting, and now they're kind of working directly on the DAGs, the directed acyclic graphs in kind of graph mode. And so that's what FX mode does as well. However, I'm going to be talking about that in a different video. It's kind of different because the nature of the model kind of changes. And then the third quantization framework is Torch Export. And Torch Export is very much a work in progress. It's very much leaning also graph-based and very much part of the Torch 2.0 ecosystem. But in this talk, I'm going to be going over the theory of eager mode, because I think a lot of people who do quantization do it in eager mode. And yeah, in the future videos, I'll be talking about FX mode, I'll be comparing it to eager mode, what are the weaknesses, what are the strengths, and also in the next video, we're going to have a very hands-on nitty-gritty coding tutorial where we're going to go deep into a ResNet and we're going to quantize it in eager mode, we're going to quantize it in FX mode, and yeah. So, hopefully you're looking forward to that. But for now, let's dive in and check out the theory on how to statically quantize a PyTorch model. And yes, I'll have a future video on dynamic quantization as well. Let's get into it. So these are going to involve some required architecture changes and why we need to make these architecture changes. Fusing modules, attaching QConfigs. QConfigs are like the recipes for quantization. So each layer is going to get its QConfigs. Then preparing the model for quantization, that's going to make the model into a model that you can toggle on fake quant, and then finally converting the model, and that's going to be a true int8 model. If you don't know what the difference is between a fake quant model and a true int8 model, I recommend my previous videos where I go into this in more detail, and I will be linking those in the description. Cool, so what are the required architecture changes if we want to take a floating point model and make it into an int8 model? Well, the first thing we're going to need is quant and DeQuantStubs. These are pretty simple. These are just like the input and output gates to the quantized parts of your model. So let's say that your entire model is quantized, then what is going to happen is that you just have a quantstub at the beginning of your model and you have a DeQuantStub at the end of your module. So a floating point tensor comes in, it reaches the quantstub, it gets converted into a quantized tensor, and then everything inside of your model will be quantized, once you've done everything that you need to do to make it quantized. And then once it reaches a DeQuantStub, it's going to be transformed back into a floating point tensor. So that's just what these do. They're pretty easy. Stubs have quantization parameters associated with them, so they'll have a scale and a 0 point if you're doing affine quantization, but DeQuantStubs are stateless. They're like relus. You can just reuse the same DeQuantStub as you want. And I'm going to give an example, like PyTorch has something called a quant wrapper class. So that's just if you don't want to go through the bother of placing quant and DeQuantStubs yourself. I would recommend placing them yourself, if only then you know exactly where they are, you get used to placing them. But this is, I'm just going to show you this because it's kind of a useful thing, at least for demonstration purposes, about how you can wrap your whole model in a quant wrapper. And it looks like this. So if you're familiar with how PyTorch code works, and this is very Pythonic in itself, this quant wrapper, the way it works is that, you initialize it with what your module is, and your module could be your entire model. It could be whatever ResNet or MobileNet or whatever network you're doing. It'll introduce that as an attribute, and then it'll just have these quantstubs and DeQuantStubs, and then literally the forward call will just be, as I mentioned, quantize, run through the module in quantized space, and then dequant, and then it returns this floating point tensor. So those are fairly easy, and they live in this torch AO quantization QuantStub and DeQuantStub. Cool. What other required architecture changes? Well, the second is FloatFunctionals. Now, FloatFunctionals are a bit more tricky to get used to, but they're also fairly simple. And the reason we need FloatFunctionals is that a lot of these standard operations like plus, minus, multiply, division, and concatenation do not work for quantized tensors. And the reason for this is, let's say, ultimately it's because we need a requantization step, but I'll give an example as to why this is the case. So let's say we have a tensor A that has a dynamic range between 0 and 1, and a tensor B which has the same dynamic range, and then you just do C equals A plus B. What quantization parameters should C have? Well, in theory, it could be the dynamic range could be from 0 to 2, right? So you could just have some sort of automatic quantization parameters where you set that automatically, it's going to be 0 to 2. But in practice, maybe, just the way that A and B work out to be is that 100% of the time, experimentally, C is just in between 0 and 1.1, in which case there's no reason to have quantization range between like 1.1 and 2. So when we do this, it would be better if it had its custom quantization parameters for that operation, so not to waste quantization space. So that is why we can't just use plus, minus, multiply, concat, etc. These all require a requantization step. The way FloatFunctionals work is that it's the same FloatFunctional class, but they have these different methods, which are add scalar, which is just adding a scalar to a tensor, mul scalar, multiplying two scalars together or adding a scalar, a concat, and an add relu. An add relu is just the same as adding two tensors together and then automatically applying a relu. Those are the only 6 FloatFunctionals that are currently supported by PyTorch. It is a bit of a pain that they don't have quantized division, like they don't support division operations currently. The way that you would do that if you need division is that, generally speaking, you would just have a DeQuantStub, then do the division in floating point space, and then requantize the output. But yeah, like that's the way you would do it. I have a potential application in the future where I might actually need quantized division, so maybe I will implement this. If I do, I will make a video on it and I will show you how I did it. The only reason it's currently not supported by FloatFunctionals is because they haven't implemented a quantized kernel for it, but if and when I do that, I will make a video on it. And this is how FloatFunctionals look. They will be initialized as this torch and then quantized FloatFunctional. It is an object, and it has this kind of weird notation that gets a bit of getting used to. So your FloatFunctional can be called anything. Here I just called it addition because eventually it will be used as an addition, but this attribute has these different methods. It has the add, it has the mul, it has the add relu, it has the concat, and depending on what operation you're doing, you're going to use these different methods. I would generally recommend, if you are using FloatFunctionals, that you wrap them in an NN module with a name that's like, if, for example, if you're using the add operation, it will be like FloatFunctional add or something, or if it would be a concat, it will be called FloatFunctional concat. In my experience, it just makes the state dict of the model easier to navigate. But that's up to you. If you just want to use the kind of native FloatFunctionals without wrapping them, that is completely up to you, but that is how they work. So, here in this case, in case it wasn't obvious, we're just adding two tensors together with this FloatFunctional. Cool. What is next? So after we've done all of the required architecture changes to our model, next it is highly recommended to fuse certain modules together. Now, the purpose of fusing modules is to minimize unnecessary requantization steps. And this does two things. One, it minimizes quantization error, which is good. And it also helps PTQ, which is also good. And it also speeds up inference, which is good. So there's not really any good reason not to fuse modules if you can, so you should. And the reason for this is that sometimes, for example, the simple cases like a linear relu or a conv relu, there's not really much point to do a conv operation and then do a requantization step and then apply a relu and then have to do another requantization step. Like it's kind of messy. The quantization parameters of the conv should be equal to the quantization parameters of the relu, and there's no reason to be doing that step twice. So PyTorch does offer these fused modules that if you have like, you know, a conv and a batch norm and a relu, you can fuse that all together into what's like a quantized conv batch norm relu. And there's different ways to do this. You can either keep the batch norm, you know, trainable in kind of QAT mode, or it can be kind of fused to be static, and then the batch norm parameters can be folded into the conv layer. But yeah, there's different ways to do this. Now, again, these are just the ones that PyTorch supports. You can fuse other layers, and I have checked this, but that requires custom quantization code. You have to write like some, you know, fused C++ kernels. There's different layers at which the fusing happens. At the highest level in PyTorch, it's just a sequential wrapper. At the lowest level, it's a custom C++ kernel. So you do kind of have to fill those in by yourself if you want to. And again, like I've checked, like you can fuse like a conv and a prelu on Intel, for example. So maybe in the future I will also be implementing a fused conv prelu. If I do, I will make a video on that as well. But yeah, and if you have plans to fuse something, you should always check that it is actually supported by the hardware you're trying to target. Like if you're going for NVIDIA or something and you do all this effort to do a conv leaky relu or something and then you find out it's not supported, you should probably check that it is actually supported by hardware first. And this is just how we do the fusing. It's really easy. It is slightly brittle. So basically there's two methods to do the fusing. One is this name-based method, which we literally just call torch quantization fuse modules, and we feed in a list of lists. So for example, conv1 and relu1 will get fused together because they are part of this first list, and then conv2 and relu2 will get fused together because they are part of that second list. There is a second method, and that is that they use a graph-based method to literally trace the model, and they just kind of fuse the modules that they can. If a conv is followed by a relu, it will fuse the conv and the relu together, which is better. It's much more robust because the naming-based method is kind of inherently fragile. If someone changes the name of a layer, it can break all of this, and then those won't get fused, and it'll probably fail silently. So this is kind of brittle, but it is the way that it is normally done. The graph-based method is much more robust. Okay, then after we've prepared, we've done the architecture changes, we've fused our models. Next, what we do is we attach QConfigs, and QConfigs are just the quantization recipe for your given layer. So for example, here in the QConfig is where we would specify, do we want symmetric quantization or affine quantization? What will be our initial quantization parameter values? How the quantization parameters will be updated? Will they be fixed? As in, you can't update them at all, or unless you do it manually. Or will they be observed via PTQ, or can they be observed and learned? So you initialize them via PTQ, but then you update them via gradient descent in QAT. So all of that can be contained in your QConfigs. They can be different for activations and for weights. You can also specify the kind of PTQ observer that you want. Do you want a min-max? Do you want a histogram? And in PyTorch, it's a nonlinear parameter search to minimize the L2 error. And sorry, there are other options as well. There's like per channel min-max. You can create your own custom PTQ observers. You can do a lot. And PTQ observers are pretty easy to code custom versions of, so I 100% will have a video on that because I have quite a lot of experience with that. And how you actually attach QConfigs in code is pretty easy. It's literally as simple as just creating this activation QConfig object. And for example, here in this case, we have taken the learnable fake-quantized class, which is one of the more, I would say, advanced classes in the PyTorch quantization library. It just means that it has quantization parameters that are learnable via gradient descent. We're going to use a PTQ observer that's a min-max observer. These are our quantization bounds. This is what our data type will be. This specifies that we're doing per tensor affine quantization. These are our initial quantization parameters, and grad scaling is related to when we learn the quantization parameters via gradient descent. There's something called grad scaling. It basically means we just divide the gradient by the size of the tensor that we're operating on. There's a paper called the Learned Step Size Quantization, which introduced learned step size quantization. It also introduced something called grad scaling. This is just kind of industry standard. You don't really need to know what this is doing, but if you are curious, then you can read the paper called Learned Step Size Quantization, and it will make reference to grad scaling. So once we have this QConfig object, then we can literally just add it. So it's as simple as you have your module, you have your QConfig, and this is literally what you call. So you create this attribute for the layer, and for activations, we're going to use this activation QConfig that we just initialized. And for weights, we're just going to default to the default observer. Just for the sake of this example, I would generally recommend that you create your own weight quantization QConfig so that you can control exactly what it's doing. But for the sake of this coding example, this will work. This is just a default. Cool. So we've done all of that work. We've added our QuantStubs and FloatFunctionals. We've used modules, which again is optional but highly recommended. We've attached our QConfigs. We are ready to go. We literally just have to call one line of code, torch quantization prepare model in place true, and it will take your model and it will turn it into a quantizable model. Now what this model is going to look like, it's still going to be a floating point model, but it's going to be, you have the option to toggle on fake quantize and, different things. So what this is going to look like is that your model state dict is basically going to look the same, but each layer, instead of just having a weight and a bias term, for example, it's also going to have two different attributes. It's going to have activation post-process and weight fake quant. The naming convention is slightly confusing. Activation post-process refers to, this is what is kind of the activation quantization object, and weight fake quant is the weight quantization object. So all in all, in kind of pseudocode, what the forward call of the layer is now going to look like is that for example, if you have a convolution, it's going to be the convolution forward where it takes in the input tensor, the weight tensor and the bias, but the weight tensor gets wrapped with this weight fake quant operation. So when the weight tensor gets called, it gets automatically quantized by this weight fake quant, which is going to do your quantization. And then the entire output of this conv layer is going to get wrapped in this activation post-process, which is going to do the requantization step. And so at the output, you're going to have a quantized tensor that was done with quantized weights, and then the requantization step. So in your activation post-process and your weight fake quant attributes, you're going to have more attributes. So for each one of them, you'll have something called observer enabled. This is a Boolean, just specifying whether or not you are doing PTQ at the moment. If this is active, it means that the quantization parameters will get updated via PTQ. You have to be careful that this is only on when you want it to be on, because intate state management can be such a pain when you're coding. So you need to make sure that this is actually only on when you want it to be on. So, be aware that that can be absolutely painful in intate. There is also, occasionally you will have, depending on what QConfig you're using, if you're using learnable fake quantize, you will also have something called static enabled. It does the exact same thing as observer enabled does in other QConfigs. I will try not to be too critical about this, because PyTorch code does a lot of really cool things and I rely on it for a lot of stuff, but there are times when I'm these don't need to be different. These should probably just be the same thing because they do the exact same thing. But anyway, just so you're aware that static enabled basically equals observer enabled. If you are using learnable fake quantize, you should be careful that if you are toggling observer enabled, there's a different method that's involved for toggling static enabled. So just be aware that that can trip you up if you're not careful. Then there's fake quant enabled, and that will basically just toggle on fake quantize. So if this is off, your layer will just output floating point layer. Like if it's fake quant enabled for the activation, it will just output a floating point activation. If fake quant enabled is false for your weights, it won't quantize the weights prior to doing the convolution or the whatever operation you're doing. And then the scale is the quantization parameter scale, and the 0 point is the quantization parameter 0 point. So those are the objects that you're going to have. You'll also have a QConfig, and then that's basically all you really need to be aware of. And then this is what the activation post-process and wave fake quant forward calls will look like. So if we go back to this slide before, when this function gets called, this is a module, but it has a forward call associated with it. And the forward call looks like this. So it takes in this floating point tensor. If observer enabled or static enabled, it will do PTQ. And then if fake quant enabled, it will fake quantize the tensor, and then it will return it. It's pretty simple. So if PTQ is off, but fake quant is on, it's just going to fake quantize your tensor with your scale and 0 point, do the kind of rounding and clamping that we've seen in previous videos, and that will be that. Finally, and just to specify, if we turn fake-quant enabled on for all of our layers, we now have a complete 100% fake-quant model. And if we, for example, only turn on fake-quant enabled for the activations, only the activations will be quantized, but the weights will be in floating point. If we turn it on for weight fake-quant, only the weights will be quantized, but the activations will be in floating point. So you can get quite a high degree of control over this. But this is still a fake quant model, it's not a true int8 model. But if we do want a true int8 model, we can take our fake quantizable model and we can call torch quantization convert. This also has an in place method if we want, and this will transform it into a true int8 model. And sometimes this will throw errors when you're converting the model or when you're trying to feed data through the model. And the common error messages will be that if you're feeding data through a converted model, often you have to transfer your tensors to CPU depending on what quantization backend you're using. I tend to use QNNPAC, and that just needs the tensors to be on CPU. Your model needs to be on CPU because, again, this is an int8 model, right? I don't know if other quantization backends will allow you to run things on the GPU or CUDA, but this is, at least in my case, it's a very common error message that the tensors need to be on CPU. So before you feed a tensor to the converted model, just send it to CPU first, and then it should be fine. You also you'll get error messages if your quant and DeQuantStubs are not in the right places. And for example, if you're trying to feed a floating point tensor directly to a quantized layer without previously going through a QuantStub, or just floating point straight to quantize, that's not going to work. That's going to throw an error. If you're trying to quantize a quantized tensor that's already quantized, that's going to throw an error. Or if you can only dequantize a tensor that's already been dequantized, that's going to throw an error. So those are very common messages or errors. Another one is that if you haven't used FloatFunctionals correctly, if you're using like a plus operation or something, that will throw an error. And then this is one that this no non-leaf tensors in the model state dict, that will actually show up even before you feed data through the model. That'll happen when you're doing this quantization, or when you're doing this conversion call. Because if there are non-leaf tensors in the model, this happens sometimes depending on how you've kind of set up your model. If you use your state dict to kind of transfer some particular training loss, or some tensor is getting temporarily stored in the state dict and it hasn't been cleared by the time you try to do this conversion, it's generally not best practice to store intermediary tensors in the model state dict, but sometimes people do this because they want to avoid using a global class or something. But this can throw an error because they are non-leaf tensors, and the deep copy operation that's part of this torch quantization convert will not function on non-leaf tensors. So that's something to be aware of. If it tells you that you have non-leaf tensors, you have to find where the non-leaf tensor is and clear it. Okay, that is it. That is the whole theory on how you actually take a PyTorch model and you quantize it. And my next video is going to be a more in-depth, actually hands-on tutorial. We're going to take a ResNet and we're going to quantize it completely from scratch. So we'll load the official ResNet in PyTorch, Torch Vision, and quantize it. So that's what I'll be doing next, but I hope this video was informative as to the theory about why we do things, what we have to do. If you liked it, please leave a like and subscribe, and if you have any questions, please put those in the comment below, and thank you. See you next time.